Welcome to my channel. So ordinary matter, all the stuff that makes up the world, is made up of atoms. Atoms are made up of what? Electrons, protons, neutrons. Now electrons are elementary particles, point mass particles. They are not made up of further fundamental particles. But neutrons and protons, as it turns out, are not elementary. They are made up of further fundamental entities which are known as quarks. So quarks are these fundamental entities that make up a class of particles known as hadrons, of which neutrons and protons are a part of. So in this video, I'm going to talk about what quarks are. I'm also going to talk about quark color hypothesis, what is quark flavor, and then what is quark confinement. But before I talk about all of these topics, let us first do a little bit of a revision from my previous video. In my previous video, I talked about the Eightfold Way. Now let's do a little bit of a revision because it will give us a flow in the entire discussion. So in my previous video, I talked about the Eightfold Way, which is an organizational scheme of organizing or grouping together different kinds of hadron particles. You see, there are a large number of these hadron particles out there. So hadrons are a class of particles that experience the strong interaction. Now, there is a huge diversity of hadron particles out there, and one very natural question that comes to mind is, are all of these particles elementary, or are they made up of further elementary particles? And this question led to the idea of Eightfold Way, which was basically arranging these hadron particles into charts or groups or geometrical patterns based on same spin but different charge and different strangeness. So for example, one grouping is the Baryon octet. So this consists of 8 lightest baryon particles having spin half. Now hadrons, as I said, are particles, subatomic particles that experience a strong interaction. But hadrons can be subdivided into 2 groups, bosons and fermions. So the bosons, which have integral spin, they do not follow the exclusion principle, are known as mesons. And the fermions, they follow the exclusion principle, are known as baryons. So 8 of the lightest baryons can be formed in this kind of an octet structure, all of them having spin half and different strangeness and different charges. Similarly, we can also arrange 9 meson particles. They all have spin 0, but they have different strangeness and different charges. There are further similar structures like the baryon decouplet, which is basically 10 baryon particles all having spin 3/2 but different strangeness and different charges. So this is basically known as the Eightfold Way, which is a way of organizing these different hadron particles into groups having same spin, each group having same spin but different charges. So the baryon octet, the meson nonad, the baryon decouplet are a few of the examples of these groupings. Now this kind of a classification scheme naturally leads to the question that, are these particles made up of something more fundamental, or are they fundamental on their own? So at this point, I want to bring to your memory the idea of the periodic table. Now, if you remember the periodic table, which consists of more than 100 different elements or atoms, but they are all essentially made up of electrons, protons, and neutrons in different combinations. So in the same way that this huge diversity of atoms can be created by recombining electrons, protons, and neutrons in different combinations, can these hadron particles be generated by recombining certain more fundamental entities? This led to the idea of the quark model. So this was an idea which was independently proposed by Murray Gell-Mann and Zweig, who said that we can perform certain mathematical calculations and say that there are certain fundamental entities having certain properties which, when they organize in certain proportions, can lead to the creation of all of these particles. So he proposed that there are 3 fundamental entities. So these 3 fundamental entities having different strangeness and different charges. So these fundamental entities are what is known as quarks. So these quarks are these supposed fundamental particles that when they combine in different proportion ends up creating those hadron particles in the first place. Now if you look at the characterization of the properties of these quarks provided by Murray-Gell-Mann, then you will see that there are right now 3 quarks up there. You have the down quark, the up quark, and the strange quark. The down and the up quark have strangeness of 0. The strange quark has a strangeness of -1, while the down and the strange quark has a charge of -1/3 and the up quark has a charge of +2/3 electronic charge. So because most of these particles have integral charges, either neutral or plus integral electronic charge or minus integral electronic charge, so the quarks which make them up need to have fractional charges. And based on this proposition of 3 quark entities, and similarly the antiparticle version of 3 anti-quark entities, we can recreate the hadron particles and explain the properties of each one of them. So essentially the quark model says this, that each baryon particle consists of 3 quarks. Similarly, each anti-baryon particle consists of 3 anti-quarks, while a meson particle is made up of a quark anti-quark pair. So based on this idea, we can recreate, let's suppose, the baryon octet as being composed of particles which are made up of 3 quarks, and the combination of up, down, and strange can be in different proportion. We can recreate the meson nonate as being composed of a quark anti-quark pair, as well as the baryon decouplet as being composed of particles which are made up of 3 different quarks. In this manner, we can recreate all the hadron particles as being created by a combination of 3 quarks or a quark anti-quark pair, and by looking at the properties of the quarks, we can explain the properties of the hadron particles themselves. So for example, if you look at the neutron, which consists of 1 up and 2 down quark. Now I told you the up quark has +2/3 electronic charge and the down quark has -1/3 electronic charge. So because the neutron has 1 up and 2 down quark, its charge should be +2/3, -1/3, -1/3, which is equal to 0. So the neutron is a neutral particle. It can have spin half. The quarks have half spin. They organize themselves in such a manner that the neutron is also a half spin particle. And because up and down are not strange particles, their strangeness is 0. You end up getting a 0 strangeness. Similarly, you can look at the proton, which has 2 up and 1 down quarks. So its charge comes out to be +2/3, +2/3, -1/3, which comes out to be 1. So proton is positively charged. Its spin is half as well as strangeness is 0. Similarly, you can also explain, let's suppose, a positive pi meson having charge +1 and strangeness of 0, and the omega particle having charge of -1 and strangeness of -3. So in a way, this idea of these fundamental entities called quarks that make up all these hadron particles is able to explain how all the diversity of hadron particles can be recreated by simply rearranging these quarks and anti-quarks in different numbers. Now, even though this kind of an idea is associated historically with the development of its own mathematical representations, but for the sake of the discussion, we do not need to go into the mathematics. I am simply telling you about the particles that constitute all these hadron particles. So as it turns out, these quarks are essentially these fundamental entities that create the hadron particles like neutrons and protons. Now, one serious problem that arose as a result of this kind of a organization of hadrons in terms of quarks is that many hadron particles consisted of more than 2 similar kind of quarks. So for example, you have a neutron that consists of 2 down quarks, a proton that consists of 2 up quarks, and more other particles that consist of more than 2 similar kind of quarks. Now, if it is that these quarks are spin half particles, then how is it that 2 of the same kind of quarks can exist inside the same particle? Now, this goes to what is known as the exclusion principle. Now, you must have heard of what the exclusion principle is. It simply states that for fermion particles or for particles having half integral spin, no more than 1 similar particle can exist in the same quantum state. Right. So if that is true, then how is this possible that 2 same kind of quarks exist inside the same particle? To get around this kind of a problem, it was suggested that maybe apart from quarks being divided into up, down and strange, there is some additional property associated with these quarks which, when they come together to form a hadron particle, is in different proportions, and this additional property is known as color. So the quark color hypothesis basically is, or was originally given to get around this idea of violating the exclusion principle of how the same kind of quarks can come together to create the hadron particles. It simply suggests that in the same way that, let's suppose you have electronic charges, okay, right? Charge is a property of particles, and this property can manifest into two different ways. You can have positive charge, you can have negative charge, and when a positive and a negative charge come together, then they create an electrically neutral whole, right? So in electromagnetism, charge is a property that can manifest in two different ways of positive and negative. So in terms of quarks, this color is a property that can manifest in 6 different ways. You can have red, green, blue, and for the anti-quarks, you can have anti-red, anti-green and anti-blue. So this is called the quark color hypothesis, and it simply states that quarks which come in 3 different forms, apart from that there is an additional property which we call as color, but this has nothing to do with visual color. Even here I am representing using the visual color of red, green and blue, but the actual property has nothing to do with ordinary visual color. It's just a naming convention, you can say. Now, why we have used this naming convention, I am going to come to that in a moment. But essentially, this is some kind of a quantum property that can be used to distinguish the quarks from one another. Now, you could have easily named these properties as, let's suppose, X, Y, Z or something like that. But the reason they have been named as red, green and blue is because it can help us in understanding how these different colors come together to create hadron particles. So for example, the analogy here is that when you talk about primary colors, when you talk about white light, it basically is composed of 3 primary colors, right? When the primary colors come together, you create white light. Now, the analogy with respect to quarks and hadron particles is that all hadron particles are supposed to be colorless. So when quarks come together to create a hadron particle, they come together in such a manner that their color properties will be either in equal proportion or will cancel each other out, so that the final hadron particle is colorless. So if you have a baryon particle, it will consist of 3 quarks which have each red, green and blue property, so that the final baryon particle is a colorless hadron particle. Can you see that? Now similarly, if you look at, let's suppose, a meson particle which consists of a quark-antiquark pair, then in that case the quark will have a particular color, let's suppose red, and the antiquark will have anti-red, so that ultimately the meson itself is colorless. In fact, all naturally occurring hadron particles are what you can say as colorless, because they do not exhibit this property. This is a property which is intrinsic to the nature of quarks only, and only when quarks come together to combine, then this property is relevant. But beyond quarks, this property is not relevant, in the sense that hadrons are colorless. So they are either composed of an equal proportion of these 3 properties, or they are composed of one color and one anticolor. In fact, this color hypothesis also explains why certain kinds of hadron particles having certain number of quarks are not found. For example, let's propose a hadron particle consisting of 2 quarks, okay? Not a meson which consists of a quark-antiquark, but rather a hadron particle consists of 2 quarks. Now, we cannot have a hadron particle consist of 2 quarks, because in that case, whatever the color of these 2 quarks are, they will not create a colorless hadron particle. So 2 quark combination of hadron particles are not found in nature, or rather 4 quark combinations. You do not have 4 quark combination of hadron particles, because even in that case, the hadrons would not be colorless. So all the hadrons, whether baryons or mesons, they are all colorless in the sense that when these quarks come together, then they cancel out, you can say in that term, the property of color so as to create a colorless hadron particle. So using this idea of color hypothesis, let's suppose if you look at the neutron, which I said consists of one up and two down quark. Now these three quarks, the up, down, down, have different colors. So now there is this additional property of color which differentiates both the down quark. Do you see that? Similarly, you have a proton which has two up and one down quark, but now all these three different quarks have different colors. Similarly, if you look at the baryon octet and the baryon decouplet, they all consist of hadrons having three quarks, but all three in each particle have the color property of red, green and blue. So ultimately all of them are colorless in that sense. And similarly, the meson, which consists of a quark anti-quark pair, is consisting of a quark having a color and an anti-quark having the anti-color. So this idea of a quark color is something which is very much inherent to the peculiarity of quarks themselves that do not manifest beyond the hadron particles to macroscopic objects, let's suppose. And in fact, this peculiar property of color is very much intrinsically linked to the idea of the strong force itself. You see, the quarks are attracted to each other because of the strong force. And the strong force, you can say, is very much dependent on this color property in the same way that, let's suppose, electromagnetic force is dependent on the charge property. So electromagnetic force has this property of charge based on which you can have attractive and repulsive forces, right? So in that same way, the strong force is intrinsic to this property of color that quarks have. In fact, the strong force is also known as the color force sometimes. Now this is all about the property of quark color, but apart from the quark color, as I said, that there are different kinds of quarks like up, down and strange, but as it turns out, today we know that there are further more kinds of quarks. Now what is this property called? This property is called flavor. You know, flavor, something tastes sweet, something tastes sour, something tastes salty. I have no idea how that name came into this differentiation of quarks, but that's how it's named. The flavor of quarks, as it turns out, is what tells us whether the quark is up, down or strange. And then you have these additional quarks, the charm, top and bottom, which are basically quarks that were discovered later on, that were found in particles, heavy particles that were formed in very high energetic nuclear reactions that were extremely unstable. So today, at this particular point in time, we know of 6 different kinds of quarks, you can say, or 6 different flavor of quarks, because this is what is known as the manifestation of the property of flavor. So you have the up quark, the down quark, the strange quark, the charm quark, the top and the bottom quark. Now of course there is a lot of mathematics and theoretical formulation behind these ideas. We cannot go there. I'm just introducing the topic here. So the quark flavor manifests in 6 different ways as 6 distinct quark particles. Now, keeping aside all these theoretical ideas of these fundamental entities constituting hadrons in different proportions coming together, experimentally, none of the quarks have been actually isolated. In the half a century of discussion on quarks, we have not yet been experimentally able to isolate and detect these quarks as individual particles. And this brings me to the topic of quark confinement. So what is quark confinement? I told you that inside a hadron particle, let's suppose a baryon, you have 3 quarks that are very much attracted to each other because of the strong interaction. So the strong interaction is a force which exists between these quarks due to their color property. So there is an exchange of particles going on between these quarks which is known as gluons. So based on the exchange of gluons between these quarks, it leads to the creation of a very strong, very powerful, in fact the strongest of all forces in these distances, the strong interaction. And it is the strong interaction that holds these quarks together inside an hadron particle. Now the nature of this force is such that you can imagine that they are being as a result of the exchange of gluon particles, but you can also, let's suppose, imagine that there is a bond or an attractive force which can be replicated by a spring, let's suppose. So if you have three quarks that are attached to each other in springs, in the sense that what I want to say is that, so if you pull the spring, then with increasing extension, the force increases, right? So the more you try to pull the spring apart, the more the force to bring it back increases. Now, of course, in real life, at some point, the spring will break apart. But what happens here? What happens when experimentally you try to break apart the quark by giving some kind of an external energy, by some sort of a high energetic nuclear reaction where you are bombarding these hadron particles with smaller particles like electrons or some other particles. So you're essentially trying to break apart this combination. But when you provide energy to it, when you try to separate these quarks, instead of the quarks being isolated, you end up creating a quark-antiquark pair. Now, let me explain to you with an example. Let's suppose that you have a neutron particle, right? The neutron has one up and two down quarks. If I provide huge amounts of energy to this neutron by, let's suppose, some kind of an external gamma photon, and I expect the gamma photon to come and break apart the neutron into its constituent quarks, what actually ends up happening is that the gamma photon, instead of breaking apart the neutron into individual quarks, the energy is used for the creation of a quark-antiquark pair. So now these combination of quarks will reshuffle. So you end up getting two up and one down quark, which will become a proton, and then you will get a one anti-up and one down quark, which will become a pi meson. So essentially, instead of the external energy breaking apart the hadron into its individual quarks, you end up getting these new particles. So the extra energy, instead of breaking apart the quarks, lead to the creation of a quark-antiquark pair, which rearrange inside the hadron to create two particles. So when a neutron is bombarded with a gamma photon, it essentially becomes a proton and a pi meson. So this is what happens with all the hadron particles. Whenever you try to bombard them with very high energetic particles, instead of the energy breaking apart the hadron, you end up creating a quark-antiquark pair, which then reorganize to create two new particles in the first place. So this is known as the idea of quark confinement. This is why we have not yet been experimentally able to isolate the quarks into individual particles. You can think of this like the idea of magnets. So if you have a magnet which has a north pole and a south pole, you cut the magnet in half. You don't get a north pole and a south pole separately, but rather you get two parts having north and south, right? The one half will have both north and south, the other half will also have both north and south. The same thing with quarks. When you try to break apart the hadron particle, instead of breaking apart the quarks, you end up creating new particles from that excess energy that you have provided. This is known as quark confinement. So that is all for today's video. I hope that you have got a little bit of an idea of what quarks are. These are the fundamental entities that make up all the hadron particles. So along with electrons, which belong to the class of particles called leptons, these quarks now constitute the fundamental particles in our universe. And apart from discussing quarks, we also talked about quark color, red, green, blue coming together, quark flavor, and quark confinement. In my next video, I will talk about the standard model in particle physics. Till then, see you. Thank you very much. Have a nice day.